Welcome. My project is entitled The New York State Shift: Hydroclimatology of a Warming Winter. From Snowbelt to Rainbelt, a 50-year case study. Over about the next 20 minutes, we're going to take a deep dive into the rapidly changing hydroclimatology of New York State. This presentation draws on extensive data from the New York State Department of Environmental Conservation and the New York State Climate Impacts Assessments, and peer-reviewed ecological and climatological studies. When we think about climate change, we often default to images of summer heat waves. However, according to the regional data we will review today, the most profound structural shifts in New York State are actually happening during the winter months. We are going to look at long-term trends of our warming winters, analyze the physical processes driving extreme weather like rain on snow events and flash flooding, and explore the subsequent impacts on the regional ecology and its economy. In short, New York is transitioning from a snow-dominated winter ecosystem to a rain-dominated one. To understand this current state of New York's climate, we must first look at the historical data. According to the Observed and Projected Climate Change in New York State Overview, published by the Department of Environmental Conservation, our statewide average annual temperature has increased by approximately 2.4 degrees Fahrenheit from 1901 to 2022. However, that average hides a much more drastic seasonal shift. The DEC report highlights that our winters have warmed at a rate of 0.34 degrees Fahrenheit per decade over that same period. This means our coldest season is warming nearly twice as fast as other seasons, like the spring and the fall. Looking forward, the DEC notes that, depending on global greenhouse gas emissions, New York State could see average temperatures climb 4.2 to 12 degrees Fahrenheit by the late 2080s. This represents a fundamental alteration of the winter season itself. This brings us to the core concept of this entire presentation: the phenomenon of the missing winter. According to New York City Department of Environmental Conservation and the Department of Environmental Conservation New York State Climate Impacts Assessment, that New York State will actually get wetter in the winter, with precipitation increasing up to 30% by the 2080s. However, because our baseline temperatures are rising so rapidly, we are increasingly crossing the 32 degree Fahrenheit threshold. As noted in the Northeast Climate Impact Assessment Overview, because of this warming, the increased moisture is going through a phase change. We are transitioning from a snow-dominated winter to a rain-dominated winter. We are getting the precipitation, but the visual, physical, and ecological landscape of snow is disappearing, leaving behind a very different environment. To help visualize this shift, I generated this chart from NOAA and SCIPP, showing the standard anomalies of temperature and precipitation in New York over the last 50 years. This chart uses z-scores to show how far each winter deviates from the long-term average. If you look at the left side of the chart, you'll see that in the 1970s and 80s, we frequently saw negative anomalies, meaning our winters were consistently colder and drier than average. But as we track the data through the 1990s and toward the present day on the right, you see a distinctive pivot. Both the blue temperature line and the red precipitation line consistently trend upward into a positive territory. This confirms the data from the DEC reporting. We are now living in a regime where almost every winter is warmer and wetter than the historical baseline of the past. Because climate is often noisy, smoothing out year-to-year variability makes the structural trend undeniable. Based on a raw data set from NOAA and SCIPP, I created this 5-year moving average temperature chart for New York. The light blue trend line represents the state's 5-year average winter temperature. In the 1970s, our moving average was safely down in the low 20s. Over the last 50 years, it has climbed steadily along the linear trend line, pushing into the upper 20s today. The Union of Concerned Scientists, a 2006 assessment on Northeast climate, warned of this exact trajectory. While the upper 20s is still technically freezing, it means our average day is now so close to 32 degrees that any minor warm front easily pushes the atmosphere into a rain-producing territory rather than a snow. Let's zoom into Albany, New York as a localized case study and see this phase change in action. Using Northeast Regional Climate data set, I plotted 3 variables simultaneously over a 50-year period for the capital region of New York State. The solid blue line confirms the DEC data, showing Albany's rising winter temperatures. The orange line tracks total winter precipitation, which is steadily and slightly increasing as well. So we have the heat and we have the moisture, but look at the dotted green trend line. That represents the count of measurable snowfall events. It is sloping directly downward over the past 50-year period. This perfectly illustrates the missing winter paradox. Outlining in our project summary, Albany is getting the same amount of winter moisture it always has, but because of the rising temperatures, that moisture is simply no longer falling as snow. New York is a large state for the Northeast, with incredibly diverse microclimates. So the impacts of this warming are highly regional. According to the Climate Impact Spotlight on the Adirondack region, our historically coldest zone is completely losing its deep freeze. Historically, a town like Lake Placid experienced over a month of sub-zero days per year. By the 2080s, the Spotlight report projects that could drop to just 2 days a year. This warming threats New York's 175 acres of rare alpine ecosystems on the high peaks, which cannot survive without extreme cold. Furthermore, the assessment notes that iconic wildlife is also threatened. The nesting cycles of the common loon are disrupted, and warming allows white-tailed deer populations to explode. These deer carry parasites that are lethal to the region's moose, potentially driving moose out of the state entirely. Conversely, down in New York City, the winter phase change is traded for a severe summer threat, extreme heat. The Climate Impact Spotlight on New York City details how the dense concentration of buildings and asphalt creates an urban heat island, making the city up to 9 degrees hotter than the surrounding areas. Historically, New York City saw about 4 days a year over 95 degrees. By the end of the century, the Spotlight reports projections up to 54 days a year over 95 degrees. When combined with high humidity, the heat index reaches extremely dangerous levels. This possesses a massive public health crisis. The city's assessment cites a 2021 study revealing that nearly 300,000 housing units lack air conditioning, placing a disproportionate burden of heat-related illnesses and mortality on low-income residents and the elderly. In the Catskills and the Hudson Valley, the dominated climate story is extreme weather. In a 2013 peer-reviewed study published in the Journal of Climate, researchers Montese and Frey analyzed over 100 years of stream gauge data in this exact region. They found that our baseline for flood risk has completely shifted. During the first decade of the 21st century, the frequency of extreme warm season precipitation and streamflow events spiked by 150 to 200% compared to previous decades. We saw the devastating reality of this during Hurricane Irene and Tropical Storm Lee, which caused unprecedented flooding. Because the Catskills feature steep, rugged terrain, the increasingly heavy rainfall documented by Montese and Frey is funneled immediately into the valleys, washing out bridges, destroying towns, and making 100-year floods a regular occurrence. The image on the right was Hurricane Irene hitting the Northeast. Lake effect snow in western New York. Western New York faces a fascinating counterintuitive paradox regarding winter warming. According to the DEC's Observed and Project Climate Change Report, as the climate has warmed, the maximum ice coverage on the Great Lakes has actually dropped by 30% between 1973 and 2008. When Arctic air masses blow over this newly exposed, relatively warm water, They suck up massive amounts of moisture, triggering extreme lake effect snow bands. The DEC notes these storms can drop up to 48 inches of snow in a single event. Therefore, in the near term, global warming is actually fueling worse localized blizzards in places like Buffalo. However, the DEC report projects that in the long term, as temperatures continue their upward trajectory, the air will become too warm to support snow, and these extreme lake effect snows will eventually transition into devastating heavy rainstorms. Moving to the coastline, the DEC Climate Overview details the severe threat of sea level rise. Along New York's ocean coast and the tidal Hudson River, sea levels have already risen by more than a foot since 1900. Under high emission scenarios, the DEC projects we could see an additional 75 inches, over 6 feet, by 2100. The danger here isn't just a slowly creeping shoreline, it is the compounding effect of storm surge. When a storm hits, the surge starts from a much higher baseline, pushing water far inland. The Climate Impact Spotlight on New York City's emphasizes that this threatens low-lying neighborhoods, endangers coastal fuel storage terminals along the Brooklyn waterfront, and threatens to submerge historical cultural sites. Specifically identifying Ellis Island and the beaches of Coney Island are highly vulnerable. So, why are we seeing these extreme floods anyway? We have to look at the process-based physics of the atmosphere. The DEC climate report points directly to the Clausius-Clapeyron relation, which dictates that warmer air can hold exponentially more water vapor. The report actually cites studies showing that for every 1 degree Fahrenheit increase in air temperature, the intensity of a sub-daily downpour increases by as much as 7%. Because New York is warming rapidly, the atmosphere is holding massive amounts of moisture and dumping it all at once. According to the DEC, this is why the Northeast leads the entire nation with a 70% increase in extreme heavy precipitation events since 1958. When a storm drops 3 inches of rain in a single hour, it completely overwhelms the urban stormwater systems, leading to instant flooding in that area. One of the most dangerous and specific hydrometeorological risks created by our warming winters is the rain-on-snow event. As outlined in the 2022 Northeastern Naturalist Study by Bergwowski and colleagues, show that our temperatures hover around the freezing line. We frequently build up a deep snowpack only for a warm rainstorm to roll in a few weeks later. The thermal energy of a warm rain rapidly melts the snowpack. However, the ground beneath the snow is often still frozen solid. Because the soil cannot absorb any water, nearly 100% of the rain, plus the water equivalent of the melted snow, instantly becomes a surface runoff. This double impact creates a massive, immediate flash flood and creates violent river ice jams that can destroy bridges, culverts, and valley infrastructure below. To visualize the physical danger of rain-on-snow events, I generated this real-world hydrograph from New York State Mesonet in our programming, analyzing a stream gauge in Walton, New York, a small town that happened to have the data needed for a specific case study. The gray bars at the bottom represent the physical depth of the snowpack, and the green line represents the river discharge rate in cubic feet per second. Notice the stark visual correlation. The massive, violent spikes in river flooding align perfectly with the sudden sheer drop-offs in the gray snow depth bars. Some interesting things to point out is what I'm talking about is right here. A lot of snow depth and then a high discharge event only followed by this. But more particularly, let's compare a summer event here, a large precip event leading to a medium discharge event. So high precip, medium discharge, and then a lower precip event in mid-December. There is snowpack, but it led to a higher discharge event at the stream. Lastly, this chart perfectly captures the signature of a rain-on-snow flood event, demonstrating exactly how volatile winter precipitation directly dictates our downstream flood severity. Our shifting winter isn't just an infrastructure problem, it is also a biological one. According to the 2022 Northeastern Naturalist study by Perwaski, our extreme winter cold snaps historically acted as a natural pesticide. As we lose those sub-zero nights, invasive species survive the winter. For example, the study notes that the hemlock woolly adelgid requires temperatures around negative 30 degrees Celsius to trigger high mortality. Of course, it doesn't get that cold, but with wind chill in the high peaks of the Adirondacks, it might be possible. Without these cold snaps, it is devastating the hemlock forests. Similarly, the study documents the southern pine beetle, which has a lethal threshold of negative 18 degrees Celsius, expanding directly into New York's red pine and eastern white pine forests. Warming winters are effectively opening the northern gates for destructive forest pests, and this could be a major issue in the future. The map on the bottom shows the southern pine beetle and how it's reaching up into New York, potentially soon. The physical loss of snow also triggers dangerous ecological cascades. Drawing again from the Northeastern Naturalist, the first cascade is the albedo feedback loop. White snow reflects solar radiance. When it melts, it exposes dark soil, which absorbs the sun's heat, warming the ground and accelerating the loss of winter. Furthermore, the Perkowitsky study details how shrinking snowpack destroys the subniveum, the insulated habitat beneath deep snow. Deep snow acts as a thermal blanket. Without it, the freezing ambient air penetrates the bare ground, and freeze-thaw cycling kills delicate tree roots, destroying essentially soil microbes, and eliminates the winter shelters required by threatening wildlife, specifically the Canadian lynx. To conclude, this climate shift carries a massive socio-economical price tag. According to the Adirondack Region Spotlight, the multi-million-dollar winter sports industry is at severe risk, with variable downhill skiing days projected to drop from 68 down to just 31 days by the mid-century. Downstate, our mass transit infrastructure is buckling. The New York City Spotlight details that during Hurricane Ida, flooding destroyed 28 buses at a single Staten Island depot, costing the city $8 million. But the most important takeaway, echoed across all sources from the DEC to the Union of Concerned Scientists, is that the worst of these end-of-century impacts can be avoided if we commit to lower emission pathways today. Understanding these hydroclimatological changes is a necessary first step towards building a resilient New York and resilient world. Thank you. Here are the primary research reports, peer-reviewed journals, and state assessments I used today to compile the data and projects presented. I do want to thank you for your time and this class. It was very informative. I learned a lot, and honestly, this might be a future field that I want to go into. I'm going to leave this slide on here for about 10 seconds. That way you can see it